Hello everyone, I'm Hao Tang from Shanghai Jiao Tong University. It's a great pleasure to give a talk on our efficient TensorFlow solver for large-scale quantum PageRank and quantum stochastic walks. So our initial motivation is that we want to implement a quantum PageRank for large-scale networks. You may have probably heard of the Google PageRank. It was raised by the Google founders and now becomes one of the most prevalent tools to rank the significance of the nodes in a website or any networks. Essentially, it uses classical random walks to navigate among the networks, and the stabilized probability distribution represents the significance of the nodes. In recent years, the quantum PageRank was raised that essentially replaces the classical random walks with the quantum stochastic walks. And the quantum PageRank had several advantages. Firstly, it avoids degenerate rankings to make them more accurate. For instance, this work did a PageRank and a quantum PageRank for this network. For node 6 and 8, the classical PageRank suggests that they have the same result, while quantum PageRank shows their differences to avoid the degenerate rankings. And meanwhile, quantum PageRank can pay attention to secondary hubs to better protect those sensitive nodes. And a practical quantum PageRank solver has to be able to work on the various large-scale networks in real life. For instance, the U.S. airline network has above 900 major U.S. airports. And for any network in real life, it's often of a large size. To work out the quantum PageRank, we need to know a bit about the quantum stochastic walk. We often use the Lindblad mass equation to describe it. It's a mass equation, and the first term is representing the quantum walk part, and the second term represents the classical random walk. We use a parameter omega to interpolate the ratio between quantum and the classical random walk. When omega is 0, it reduces to the pure quantum walk, which can also be calculated using the wave function. And when omega is 1, then it becomes the pure classical random walk. So such Lindblad mass equations is often used to describe those open quantum systems that widely exist in biology, neural networks, condensed matter physics, and so on. And typical case studies include the energy transport and the quantum PageRank. To study quantum stochastic walks, we can implement it in hardware or use software simulation. And for the hardware implementations, in recent years, it develops very quickly. It has been implemented in different systems like integrated photonic lattice, which is the system that I am working on, and the programmable MZI interferometer array, and NMR, and superconducting circuits. They have reported different sizes and different advantages. And the key point is that they have to introduce the classical noise term in whatever the quantum system is. So they use different ways to introduce the decoherence. For the large-scale integrated photonic chip, as an example, we currently have managed to use the large capacity of the photonic chip. In the past 2 years, we managed to demonstrate the first real spatial 2D quantum walks and the first demonstration of quantum fast heating in experiment. And we further utilize this capacity to implement quantum stochastic walk by introducing random detunings along this waveguide for the propagation constant. So even for the scalable integrated photonics, there's still actually some geometric constraints because we use the spacing to represent the strength of the couplings. For certain configurations, it can be easily mapped into the 3D structures. But still, for other arbitrary Hamiltonian designs, maybe it's still challenging to implement it in this lattice. So it's still meaningful to have numerical simulators of quantum stochastic works on classical computers for any arbitrary Hamiltonians. Essentially, it is to solve this Lindblad equations. We first vectorize rho and use Kronecker product like this. So the whole term represent this exponential part put here, and then this rho can be solved using the exponential matrix method. Worth to note that the Kronecker product will expand the space from On squared into On to the power of 4, so it will consume a lot of memory. Currently, there have been several numeric solvers for quantum stochastic works. Q-tip is famous, but it's not tailored for quantum stochastic works on graphs. And there is a good one for graphs named QS-work using Mathematica, but it uses built-in function from Mathematica, which does not have any optimization for the memories, so it very heavily consumes the memory. And last year, there's a junior version of the quantum stochastic work solvers, and it improves this functions a bit. And our solver, using combining this Runge-Kutta method and GPU parallel computing, manages to reduce the memory from On power 4 to On squared and greatly reduce the required time as well. This work has been accepted by Science Bulletin and will be coming out soon. And recently, we also noticed that a work from Professor Jimbo Wan in Australia group, they have done an excellent work. Also reduce the memory to N squared, and they conduct parallel computing using high-performance computers, where we use the GPU parallel computing. So we see that different groups are now making efforts to improve the efficiency of quantum stochastic work numerical solvers. Here's how we do it. We notice that although C is a matrix consisting of n4 elements, they each can be obtained from the information of On squared. So here, this is a matrix of On to the power of 4, and we use Runge-Kutta method to reduce the memory, because now we make this large matrix divided into n squared slots, and each slot can be used to calculate each component of the row vector. So the memory's consumption will reduce from On to power 4 into On squared for each slot calculation. But meanwhile, this will require us to calculate it n squared times for these n squared slots. Fortunately, for matrix calculations, the sequence of each slot doesn't affect the final result. So we can load the calculation of each slot into each of the many processing units of GPU, and then conduct GPU parallel computing to calculate those slots simultaneously. And this reduces the time greatly. Here's a little bit more introduction of the Runge-Kutta method for those who haven't heard about it. So, it calculates this time evolution by breaks down the time into many segments, and each with a size h. K1, K2, K3, K4 are those slope parameters. And then this term is like a weighted slope for the whole range. So this yn plus 1 can be calculated by timing this, multiplying the h with the slope. And this is a typical RK4 four-step method, and we use the RKF45 with an adaptive step size h, And we analyze the time complexity for complete graph, Erdos-Renyi graph, and pure quantum walk. And this can be further reduced by using the TensorFlow parallel computing. Here is the performance for detailed examples. For this Erdos-Renyi graph, we see the yellow lines shows our result because it reduces the memory from n4 to n squared. So we see now it just consumes a memory of like 200 MB, which can easily be done in normal computers. And for the time, this is for the CPU calculation, and this for GPU calculations. We see that for GPU calculations, for 1,000 node, it reduces to only a few seconds. So comparing to the QS Warp, a prevalent Mathematica solver, our solver for the same Erdos-Renyi graph reduces to memory to only 0.2% and 0.05%. Now it can finally be efficiently calculated using normal computer and within a few seconds, which is very useful. Applying this solver to a real case, we managed to get the ranking of the US airport. And here are the results using PageRank and the quantum PageRank. And we see that PageRank always gets more average result. In that case, they don't really classify the main hub, secondary hub, or rest nodes that clearly. Well, for our case, using quantum PageRank, we see 11 as a main hub and 6 as a secondary hub. And in this case, it gets better classifications of this airport ranking case. And for this PageRank, our solver can just input the connection profile. Like this airport connects the other net airport, and the connection profile is taken as an input. The users can also input the Hamiltonians instead of the connection file. So, for this general quantum stochastic walk, these users can input the Hamiltonians for an arbitrary graph. In this case, we did a fast heating glued tree graph with a branch rate of 3 and a layer depth of 6. It has totally more than 2,000 nodes. And we want to see how the fast heating result changes with the classical decoherence terms. And we calculated 12 times for 12 cases of omegas. And it's quite worth noting that intuitively, for getting the time evolution, we need to calculate the time separately for different time, and then we get the final evolution results. So that we have to calculate many times for each single omega. But in our case, remember the Runge-Kutta method is to get the time evolution by breaking it into many segments. So we actually just need to define the final time we want to calculate, and then we can retrieve the whole result along this time. So our method is very efficient to calculate the time dynamics. Looking into the future, we want to find more applications of our solvers in biology, physics, and computer science, and so on. For instance, in this paper, they suggest that quantum stochastic walk can be used to simulate associative memory of Hopfield networks and can be applied to pattern recognition. They demonstrate a pattern recognition case for 2 times 2 times 2 cube. But in the real case, we can have it for the 256, 256, and 256 nodes for the real color cube. And that will require a lot of node numbers. And this is work done 4 years ago in Nature Materials. It's a mainly experimental work of energy transport of M13 virus. And they use this quantum stochastic walk to analyze the case, and they just analyzed the donor to acceptor ratio up to 1,000 to 1, If with our efficient solver we can use the node number up to a few thousands, then we can analyze the donor to acceptor ratio for a much larger case and to have better simulation of this energy transport issue. And we would also like to explore the non-Markovian quantum stochastic work, as it is very important for this quantum biology. And we will also like to carry on our experimental work on quantum stochastic works in the integrated photonic chips. We have done simulations of associative memory, and we would like to carry on more applications in pattern recognition using our photonic chip. And we would like to analyze the energy transport and form higher random unitary randomness in these photonic chips. So that's all of the talk. Thank you for listening.